Welcome to our fifth presentation on JetBlue. In our earlier presentations, we talked about JetBlue hedging with options contracts, but now we're going to talk about JetBlue hedging with forward contracts or futures contracts. Our agenda is going to be to discuss what forward and futures contracts are, explain some terms. Then we're going to take those concepts and estimate an optimal hedge ratio, estimate how many hedge contracts JetBlue wants to enter into. And then we're going to do an example in which JetBlue is exposed to a couple of risks. It's exposed to fluctuations, obviously, in jet fuel prices, as well as to some volume risk. We're going to consider the impact of JetBlue being hedged or unhedged, and in later presentations, we're going to try to expand that to how we could account for many, many scenarios, not just a high and low jet fuel price scenario. So first of all, let's talk about some concepts. First of all, what is a forward contract? A forward contract is just an agreement to transact in the future. It's different to a call option or a put option because both parties have to go ahead with the deal. Whereas with a call option or a put option, only the person who is the option holder, that is the person who buys the option contract, has the option to proceed with the deal. That person can force the other party to go ahead. A futures contract is a standardized forward contract. The benefits of standardization is liquidity. Once you've got a standardized contract, and even just an ordinary share is a version of a standardized contract, then you have something which can easily be traded on an exchange because people can walk into that exchange, or of course in a virtual world, log into a computer. They know exactly what the terms of the contract are going to be. Whether a forward contract or a futures contract is better in a particular situation depends upon the context of that situation. If you have two counterparties that need a particularly bespoke contract, that means the contract has to take into account their particular circumstances, they would likely want to enter into a forward contract. If you have two parties that don't necessarily need a contract to tailor to their circumstances and a standardized contract is going to meet their hedging requirements, they would have a preference for a futures contract. The other advantage of a futures contract, apart from liquidity, is that the clearinghouse in the middle is going to cover the default risk of the buyer and seller of the futures contract. Whereas with a forward contract, the counterparties are exposed to the risk that the other party might default. Now, if those parties were trustworthy, they had confidence that the other person was going to meet that person's obligations, that default risk might not be a problem. But again, that reduces the pool of people at which you are prepared to contract with. Whereas if I have a futures contract traded on an exchange, I have a very large number of people who I could potentially trade with because I'm not concerned about their individual default risks. For our purposes, because this is only an introduction to derivatives, we're going to treat all contracts, futures contracts and forward contracts, as the same. In a practical sense, the difference is that when you enter into a futures contract, you might have to post a margin, for example, 10% of your risk exposure, to the clearinghouse. That means that there is some pool of money that the clearinghouse can use to cover positions of people who might default on the contract. But we're not going to cover those margin requirements, and therefore forwards contracts and futures contracts for our purposes are going to be identical. Well, let's consider JetBlue. The first thing we're going to do computationally is determine the hedge ratio. We're going to construct a situation and ask ourselves, how many futures contracts should JetBlue enter into in order to mitigate its exposure to fluctuations in jet fuel prices? Specifically, to address that question, we're going to run a regression. And that regression is going to be to estimate the relationship between the percentage change in jet fuel prices on a monthly basis over a 5-year period from 2007 to 2011 against the percentage change in the price of WTI oil on a month-to-month basis. That slope of that line of best fit, that's going to be our hedge ratio. And we're going to come up with an equation which allows us to use the hedge ratio to determine the number of futures contracts to enter into. The reason we're going to run this regression is that JetBlue is going to hedge its exposure using futures contracts on WTI oil rather than futures contracts on jet fuel. For reasons which I don't fully understand, there is not great liquidity in futures contracts for jet fuel, but there is a high degree of liquidity in WTI oil prices. Recall that WTI oil just stands for West Texas Intermediate Oil, which has somewhat different properties to Brent oil, which is more commonly traded in Europe, and Tapis oil, which is more commonly traded in Asia. On average, those prices are about the same, but they do have some local characteristics to the markets in the United States, Europe, and Asia. And so at different points in time, their prices deviate. But that's beside the issues that we're going to confront. The issue facing JetBlue is that the jet fuel price doesn't move in perfect sync with the price of WTI oil. So there's going to be what we call basis risk. Basis risk, in simple terms, just means that your underlying risk exposure, which is fluctuations in the price of jet fuel, is not necessarily the same as the fluctuations in the price of the commodity that you're going to hedge with. So I'm going to run that through that regression with you, and you should replicate the computations that I'm performing on your computer. So pause the video at different points in time, replicate the computations, and then restart. Now we could run a regression in which we just have on the left-hand side, that is the dependent variable, just the jet fuel price in dollar terms, dollars per gallon, and on the right-hand side of this regression, just the WTI oil price in dollar terms, dollars per barrel. We could run that regression, but often when you run regressions using levels, that is the level of jet fuel or the level of WTI oil, you can get a spurious relationship. So for example, I say down the bottom of the slide that oil prices are higher today than they were 50 years ago. Wages, rent, and gross domestic product are also higher. So is the price of college tuition. So is the price of many things that we purchase. So you've got a number of economic variables which drift upwards over time, but they're not necessarily have any underlying relationship. There is some common factor which causes those underlying variables to drift upwards, including inflation, but you wouldn't necessarily say that college tuition is a predictor of jet fuel prices. In statistical terms, what that means is that your underlying variables are not mean variance stationary. What that means is that if you take a sample of data over time, you want the average for your independent and dependent variables, that is the mean, to be roughly the same in different regimes, different time periods, and you want the volatility of those dependent and independent variables to be roughly the same during different time periods. Whereas if I look at the price of oil 50 years ago versus the price of oil today, they have very different averages because of inflation. If I look at the price of jet fuel, it has a different average 50 years ago compared to today because of inflation. And if I do a plot in which I've got oil on the horizontal axis and jet fuel on the vertical axis, and both of these commodities are just drifting upwards over time, I could identify that there's a positive relationship between those variables, but it could be spurious. Just like I could plot jet fuel over time, and I could plot college tuition over time, both of those variables might be drifting upwards. There could be a positive relationship between those variables, but we wouldn't say there's an economically meaningful relationship in truth. And that's because the average and the volatility of those variables is not in fact approximately the same during different regimes, different time periods. But if we do percentage changes in our variables, like percentage changes in the jet fuel price from one month to the next, and percentage changes in the WTI oil price from one month to the next, those percentage changes are going to be roughly the same from one regime to the next. The oil price is going to drift upwards at roughly, the percentage change on average in oil is going to be roughly the inflation rate over time, and the percentage change in the jet fuel price on average is going to be roughly equal to inflation. So the average of our dependent and independent variables is going to be about the same in different time periods, and the volatility of the jet fuel price and the oil price is going to be roughly the same in different time periods. Yes, there's some high volatility periods and some low volatility periods, but they're not systematically changing in different blocks of time. So we can say that approximately we've got a reasonable basis for running a relationship between jet fuel price and oil price as percentage changes every month. You might also see that our regression equation has no intercept term. We've just got a slope coefficient, which we're going to call the hedge ratio, and that constraining the intercept equal to 0 is going to allow us to directly compute the number of futures contracts to hedge JetBlue's fuel price exposure. So let's run this regression and let's see what it means for the number of futures contracts to write. What you can see here in the presentation is the outcome of running a regression of percentage changes in the energy spot price, which is the WTI oil price, versus percentage changes in jet fuel. Each of the data points represents an individual month, and there are 60 months in that 5-year period. This line here is the line of best fit. The slope of the line is 0.81, and the R squared is 79%, and I'm going to explain those concepts. When you run a regression, the computer works out what intercept term, which we've constrained to 0 here, so the computer doesn't have discretion there, and what slope of the line minimises the sum of the squared error terms. What that means is that each of these gaps between an actual month of percentage change in energy spot price and percentage change in jet fuel and the line of best fit, that represents an error term. The computer comes up with one line that if you took the squared error term and added them up across all the data points, what slope of the line would end up with the smallest sum of squared errors. And that's why regression is often more formally called ordinary least squares regression. So we're going to replicate this outcome to come up with this 0.81 slope of the line. And we're going to use that using a scatter plot and a couple of equations in our spreadsheet. What does the R squared mean? R squared represents how much of the month-to-month movement in the jet fuel price can be explained by the month-to-month movement in the WTI oil price. 79% means that 79% of the fluctuations in the jet fuel price from one month to the next can be associated with fluctuations in the WTI oil price. So higher oil prices means higher jet fuel prices and vice versa. There is 21% of the fluctuations in the jet fuel price which can't be explained by fluctuations in the WTI oil price. There's 21% of that movement of jet fuel which is explained by something particular to the airline industry, something in particular to the refining industry, right? Something which we can't explain by the underlying commodity, WTI oil. One caveat, when you constrain an intercept to be 0 in a regression, you distort the R squared. So you, in fact, slightly inflate the explanatory power of the regression. That doesn't affect us. You should just be aware that technically we've got a slightly inflated version of the R squared, so we're slightly overestimating the explanatory power of movements in the oil price. Second caveat, this regression analysis using historical data isn't necessarily the only way that you can come up with a decision on the hedge ratio. There are more sophisticated simulation techniques we can use to come up with a hedge ratio. But at this stage, you've been covering derivatives for about 5 hours now. Maybe, we should leave that more sophisticated analysis till you've had some more exposure to derivatives. But we want to point out that you don't just want to mechanically look at historical relationships between variables and assume that those historical relationships necessarily persist into the future. And that's where simulation analysis can sometimes come in handy, because you can model potential changes in the relationship between X and Y. Okay, so let's first of all come up with this regression line, and then in another presentation I will use that 0.81 slope in order to come up with the right number of futures contracts that JetBlue wants to enter into to mitigate its exposure. I'm going to end that PowerPoint presentation and turn to our spreadsheet. you have two versions of the spreadsheet. You have a before class version of the spreadsheet and you have an after class version of the spreadsheet. I'm going to go to the before class version and I'm going to replicate chart 1 that you can see on the screen right now. So I'm going to go to the data tab and I'm going to replicate that scatter plot. In the data tab, in columns I and J, you have a computation of the percentage change in the WTI oil price and the percentage change in the jet fuel price from 1 month to the next. To create the scatter plot, I'm going to highlight all of the cells from 2007 to 2011. So I'm going to highlight 5 years of monthly percentage changes, and then I'm going to go to Insert Charts, and I'm going to find the Scatter Plot option. Click on that first scatter there. To keep things a bit neater in my file, I'm going to right-click on that plot, and I'm going to move that chart to a separate worksheet. Then I'm going to click on the data. And if I click on the data, I can see that in that formula bar, that first series of data is in column I from the spreadsheet. That was the percentage change in the WTI oil price. And the second set of data is from column J. That was the percentage change in the jet fuel price. So I want to make sure that I've got my X variable, also called my independent variable, correctly specified as I, column I, and my dependent variable correctly specified as column J. That's the jet fuel price, or the percentage change in the jet fuel price. So if I click on the data, and in particular if I right click on the data, I'm going to add a trend line. And I'm going to specify a couple of options here. I'm going to set the intercept to be equal to 0. I'm going to click the option to display the equation on the chart. And then I'm going to click the option to display the R² value on the chart. And if I blow up that information with a bigger font, you can see that we have an equation that says y equals 0.8121x and the R² is 0.7866. So what that means is that the percentage change in the jet fuel price equals 0.8121 times the percentage change in the WTI oil price. That was the equation that you saw earlier. And we have an R² of 0.79. Now, I could make that chart present a bit neater for my audience, which I've done in chart 1 of your spreadsheet. If you want information about how to present those charts more neatly, just give me a call or send me an email and we'll go through it. It's probably easier if we work it through it together on a screen, but we're not going to worry about that finesse when we do this presentation. So we're at the stage where we've replicated this particular chart in our PowerPoint presentation. How would I then take that equation, percentage change in jet fuel price equals 0.81 times percentage change in WTI oil, and convert that into the number of contracts to write? So I'm going to show you a very particular equation that I want you to implement. Here is the equation for the number of hedged contracts. The equation says is that the number of contracts that we want to write is going to be equal to the jet fuel volume that we want to hedge times the regression coefficient multiplied by the jet fuel price divided by the strike price of the forward contract. Now in our example, we are going to hedge 20 million gallons on a monthly basis of jet fuel, and the jet fuel price is currently $3 per gallon. JetBlue wouldn't necessarily hedge all of its fuel volume. Maybe JetBlue only wants to hedge a portion of its volume. And if you saw our discussion earlier, in which we compared the hedging of different airlines in Europe, the United States and Asia, you see that they have different views on how much of their exposure to hedge. You only want to engage in enough hedging to offset a risk which is material, in which it is a risk which is going to have some long-term consequences, and those consequences are asymmetric in nature. That means that the negative impact to the shareholders could be greater than the positive impact to the shareholders of the underlying commodity moving in the opposite direction. Now for JetBlue, it might be the case that a massive jump in the jet fuel price means that JetBlue becomes financially distressed because JetBlue has sold many tickets well in advance at some fixed price. And if JetBlue becomes financially distressed, maybe sales will suffer because people are worried about whether JetBlue will keep flying, maybe important maintenance and IT expenditure is cut, and maybe employees start behaving in a suboptimal manner for JetBlue by looking for work elsewhere. So they're behaving in an optimal manner for themselves, but not for the corporation. Suppose that we apply those assumptions to futures contracts that have a strike price of $100 per barrel. We've got a regression coefficient of 0.81. That tells us that the number of contracts is going to be 20 million gallons of jet fuel times the hedge ratio of 0.81 times a $3 per gallon jet fuel price divided by a $100 per barrel of oil, dollars per barrel of oil as a strike price of the forward contract. That's going to tell us that JetBlue wants to buy 487,000 WTI oil futures contracts. Now, when we get into some financial information, we're going to see that if JetBlue correctly predicted the volume, and if future fluctuations in the percentage price of jet fuel match that historical relationship, that number of futures contracts is going to give us a perfect hedge. Now, in reality, it won't be a perfect hedge because there will be uncertainty about volume, and there won't necessarily have changes in the price of jet fuel match changes in the price of WTI oil that are consistent with what we have observed on average during that period from 2007 to 2011. But if we didn't have volume risk, and if we didn't have uncertainty about the future relationship between these commodities, the optimal number of contracts to buy would be 0.487 million. So next we're going to consider regression in a couple of different ways using equations, and then we're going to consider financial impacts. That's a good point to pause, and I will see you then.